I mentioned before about the advantage of some of the newer machinery and the auto calibration process. This is kind of a neat example that shows one operator. You have 3 drivers. We've got one operator calibrating 3 machines at the same time. Because they have an automatic shutoff, in this scenario, he's just making sure that everything is set right. We've started them at different times, so they're going to end. He can collect his data. You can see the machine on the far right-hand side is almost finished. The one in the middle is a little bit lower, and the one on the far left has just begun its calibration. So there's pretty good aggregate load still in the machine. Convenient, not necessary, but sure as heck makes life easier when you have this feature. So we've completed our aggregate calibrations. We did our 3 gate settings. We've recorded all the data on our calibration sheet. We'll run through the exercise on that a little bit later. Now we're going to calibrate the emulsion. When we calibrate emulsion, we want the hopper completely empty. We don't want any aggregate in there. We're going to be running the conveyor belt for our accuracy of the connection. On the older machines that have a mechanical linkage between those, that's tied together. On the newer machines, they are electronically synchronized. So again, want to make sure that we don't have any aggregate in there. We're filling the machine with emulsion. We want it full so we can run as much calibration as possible without having to get additional weighing of the machine. Some folks, if they have multiple machines, will calibrate from one truck to another. So as they're emptying one truck, they're filling the next one. That's a very efficient process. Here you'll see that they're actually kind of hard to tell, but they're pulling out of a tanker and filling the machine from a tanker. Our scales again. So we went through, filled the machine. We're going through to the scales to get a full weight of the machine. So that's a pretty simple process. As you exit the scales, you typically will get either a scale tag or maybe at least you're writing down what the weight that you just scaled out at. Here we're writing it on our calibration sheet so we can keep track of it. Our full weight in this exercise was 42,340 pounds. All right, here is our automatic calibration screen on the machine. As I mentioned before, some of the newer machines have this automatic operation. Sure does make calibration a lot easier. If your machine is equipped with this, load the number of desired head pulley revolutions you're wanting to run. In our example, we are running 100, so we'd load in 100 as the set point and push start. This feature will automatically stop when it gets to the end. Again, if your machine does not have this feature, just run and keep track of your head pulley revolutions. That is our number that we are measuring everything against. So run 100 counts, and we get to that point, stop. It's important to keep in mind, may address this a little bit later, but if you there's different ways that folks tie in to calibrate get the material off of the machine. A lot of machines they've got a discharge valve, which is a manual valve that you open and close. You'll need an additional person down there that you're timing with for accuracy. If you don't have this, there's you can run the chance of siphoning material off, and your accuracy of your count will not be correct. If you're unsure at all about how that process would be, contact your machine manufacturer and they will give you the best recommendations for that machine. Okay, thank you. So here's a great example of a contractor that is being very efficient with their calibration process. We have to fill the machines anyway, so they are calibrating from one full truck to an empty truck. So when they're done, they're ready to go get the full weight on the empty truck and start the calibration on that one. If you've got a third truck, you would, pump onto that one. In this scenario here, As I mentioned, you see the gentleman in the yellow reflective vest. That person is right by the discharge valve. So when they started the emulsion pump, as soon as they started, they opened that valve. So there was no siphoning of the material or draining of the material. As soon as they hit their desired counts, they want to close that valve so that they can keep the amount of material discharge as accurate as possible. Kind of good looking machines too. Look at that. Alrighty, we went across our scales. We weighed our vehicle, and our empty weight was 40,900 pounds. We did 100 count revolution. So as we run all of these in a later screen, you'll see that the numbers come through. The accuracy here, again, you're typically, because we're running the emulsion pumps, their accuracy is usually very, very high. The consistency of the pumps rarely change by very much. Since we have to repeat the process 3 times, so the same thing with the aggregates, 3 times at each gate setting. Well, this is 3 times with the emulsion. That gives us our accuracy. We can see if we're off on our scales. That's good. In this particular example, this contractor is calibrating to back to the emulsion tanker. So they are pumping back to the tanker instead of into an additional truck. So we did our 3 cycles. We did our 3 times across the scale, 4 times if you consider full weight. We've got our information. We're getting it loaded in here. So we had the 42,340 pounds full, 40,900 empty, gives us a net weight of 1,440 pounds. 100 revolutions. Again, that's pretty simple when we keep it at that number. You're looking at 14.4 pounds per head pulley revolution, and that's of the emulsion. Our empty weight is now our full weight for our second evolution. Our empty weight here was 39,460. Look at that. We got another 1440 on the empty weight. 100 revolutions, we're at 14.4. And our last, because we were low on oil, we were too low, we needed to go fill the machine, so we have a different full weight. So I've got 41,800 pounds. Our empty weight was 40,360, and we hit that magic 1440. Again, historically, these numbers are usually very, very consistent. Only variation would be probably just a scale swing. We're off a little bit on the scale. But we are here at 14.4, and our average of the 3, gosh, look at that, 14.4. That was pretty amazing. And we want to calibrate the different components. Here we're going to look at the cement. So we're on this particular machine, the fine speeder is right at the very far back of the machine. They are going to be loading it with their Portland cement. When you're doing this, it's always, you can't stress enough that you're doing things in a safe manner and following the machine manufacturer's recommendations. We don't want anyone to get hurt. Okay. Again, we're staying consistent with the screen of this particular machine. Again, different manufacturers have different configuration, and their operator's manual should define this process very clearly. We're going to manually operate the fine speeder. We're going to reset our counter to 0. We're going to start the calibration process. We're going to watch the counter and stop once we reach our desired number of counts. We're going to talk about that here in detail. The concept here is the same, but the process is very different. Here we're using a small container. We're going to weigh the empty container on a gram scale. We're going to weigh the empty container so we know exactly how much the device is. we're going to run our calibration process. So we have our containment device underneath the discharge of the fines feeder. We're running for a desired number of counts, and then we're going to weigh our full container to determine how much material we were discharged from the fines feeder at that given amount of counts. So in this scenario, it's a little bit backwards because our empty weight was our container. That was 1.8 pounds. Our full weight was 14.3. And so that gives us a 12.5 total pounds. We did a 10 count. So our average pound of cement per count, per revolution, is 1.25. And then we'll repeat that process 3 times. So their accuracy is good. 3 allows you to identify if you have an anomaly, something's off. Okay, very simple and straightforward process, but important to do. Okay, we've covered the how we calibrate. Now it's when do we calibrate. This is another very important consideration because, again, the time invested to calibrate is not insignificant. It takes a little bit of effort to calibrate the machinery. We want to make sure that we're doing it for the right reasons and we're not wasting money. And that's what this time is. We've got to make sure that we're using this time wisely and for a good purpose. So calibration should occur every time you make a change to a new material, you change a related component on the machine, or you suspect that you're having a problem. We can spot check ourselves with small calibrations and single cycles if we have solid calibration numbers to compare to. A lot of folks at the beginning of a season will bring the crew back. It's good training for the folks to get kind of back up to speed and familiar with the machines. If you've brought on new people, it's a great time for familiarization. But we do the calibration of the different materials at that time so that you've got a good basis of different materials you're going to be using. Most of our markets are fairly mature in the United States, so you know usually what material, what aggregate sources you're going to be using, what emulsion suppliers you've got, those things pretty well dialed in. If not, that will come pretty quickly in time. So calibrations can be time consuming, so many companies fail to calibrate often, if at all. I have run into folks who just don't calibrate, they don't see a value in it, and it's fairly sad. I mean, it hurts you in the long run because when problems occur, in the real world they do, it's going to happen. Calibrations allow you to know where the heck you're at. The process is a valuable tool to ensure machinery is performing correctly and your materials are blended to the correct ratios. If the calibration or something is wrong with the machine, maybe we've got a partial blockage in the in an emulsion pipe, or we have something affecting the machine, that can absolutely affect the material. And if you don't know your calibrations, you don't know where you're at. You could be looking at it, you thinking that you have a material problem, you have a machine problem, or vice versa. Okay, this is typical for state specs. They usually call for calibrations to be done at least annually with each material that you're using. If you follow the ISSA specs, which we will talk about in a minute, you must calibrate much more frequently. Again, we as an industry are trying to elevate the quality of the materials so that they are used far and wide and people can see the values in the material. If we fail to have good material that we are putting on the streets, we're not going to be invited back to play anymore. So it's very, very valuable for the industry as a whole that we are, doing the right things and doing our calibrations and investing in the things to make our results, but the industry results perform. Okay. This is due to possible changes in aggregate plant at the aggregate plant, resulting in different gradation changes. That's right, a real life scenario that can happen. Changes in aggregate source within the plant, resulting in specific gravity of the rock change. All rocks are different. If you got a large quarry and they are now pulling from a different part of the quarry, the rock can change. It can be different. Those things can affect us and can make it absolutely maddening for a company to be chasing themselves trying to find figure out what the problem is. These calibrations are it's hard to make this type of class exciting, but it's really valuable. It's very important to do. Okay. Changes in asphalt base supply resulting in emulsion changes. This is factual, but in reality it wouldn't change enough to make a significant difference. But the changes in our raw materials can affect the performance. The changes in a machine can affect performance. Environmental conditions can affect performance, so it's valuable. Okay. As I said a minute ago, the ISSA standards, we are adhering to the A105 and the A143. It depends on whether they're doing the slurry or microsurfacing. So what's written in here, and I'll point out a couple things here in a moment, but it says calibration. Each mixing unit is to be used in performance with the work shall be calibrated and present in the presence of an inspector prior to the start of the project. Previous calibration documentation covering the exact materials to be used may be acceptable, provided the calibration was performed during the previous 60 days. The documentation shall include an individual calibration of each material at various settings, which can be related to the machine's metering devices. Any equipment replaced affecting material proportioning requires that the machine be recalibrated. Earlier I had mentioned replacing the emulsion pump, right? That doesn't happen often, but it was a good example. Something that would directly affect the raw ingredients going into the machine. Okay? No machine is to be allowed to work on a project until the calibration has been accepted. ISSA Inspector's Manual describes a method of machine calibration, like what we're describing here. ISSA contractors and or machine manufacturers may also provide methods of machine calibration. We are talking about a very typical historical process. New machines are being creative and coming up with different ways to do this. Refer to your machine manufacturer if it is different than a standard process, and they will give you the details on how to do that and do it effectively. The things to jump out here is, the previous calibration acceptable if it's been performed in the last 60 days. And then no machine will be allowed to work on a project until the calibration has been accepted. Again, these are industry standards from the ISSA to help us perform and put better materials on the road surface. We're getting a little closer to some of the fun stuff here. It says, what is bulking? We've got a little demonstration to show, and it's neat to see what can happen and why, when we're looking at moisture content, the value in it. Why does that matter? Why do I even care? So with the demonstration, I think hopefully you'll understand and see why we need to understand that number and consider it when we're working with our mix design, our gate settings, why we need to plug it into our calibration worksheet. The volume increase of fine aggregate due to the presence of moisture content is known as bulking. Fine aggregates will bulk more compared to coarse aggregates, and extremely fine aggregates, particularly the manufactured fine aggregates, bulks as much as 40%. There's a significant increase in the volume of the material when we add the moisture content to the rock. And you again, hopefully the demonstration will make that very clear, that so you can appreciate why this is valuable. If you want to understand more of the details on what bulking is, here is the standard for testing for bulking. We're going to do our example using the instructions from this so that we are consistent with this this process, so that you can see it is a technical bulletin that details what that is. And here's again an example. What causes bulking of aggregate? Good question. The moisture presence in aggregate forms a film around each particle. These films of moisture exert a force known as surface tension on each particle. Due to this surface tension, the particles get kind of pushed away from each other. Because of this, no direct contact is possible among individual particles, and this causes bulking of the volume. So the moisture gets in between the small particles. We said that the fine aggregates will bulk more than larger aggregates because there's more surface contact, right? There's more surface on this on all of the small particles together, and they get pushed away by that moisture. Bulking of aggregate is dependent upon two factors: percentage of moisture content. We're going to see the following moisture content example. The quantity of small particles in the fine aggregate. Okay, the more particles, the more boundary layers, the more room between more particles, the more bulking.
We're going to start the demonstration of the bulking of aggregate. We have some pre-measured and pre-dried aggregate. This is a type 2 slurry aggregate. This is 400 grams. So I'm going to take this container and I'm going to dump it loosely into here so that you can see what's going to happen as we move forward. So we take it, dump our aggregate in here. You can tell by the dust how dry the aggregate is. We're going to take the aggregate and we're going to scrape it back in the container. This is the exact process we're going to do as we add the moisture content to these other steps. We're taking care to do this over a container. Here we've got just a tray, so any lost aggregates can easily be captured and put back into our container. The process, and if you read the technical bulletin, we are doing it the exact same way. We are not trying to pack the material in. We're going to try to just put it in the material, into the container, just precisely the way we're doing it now. I'm going to take the last little bit of aggregate here so we don't lose it. We're going to put it back in. So you can see how full the container is. This is completely dry aggregate. We're going to take the same material, we're going to put it in our container. Okay. Now we're going to add 2% moisture. So we've got 400 grams of aggregate, so we're adding 8 grams of moisture. We're adding that in there. So you can see. So that's 2%. We want to mix it up so that water has a chance to cover equally, the particles. So we have a true 2% moisture content of our aggregate as a whole. So we're mixing it up. Kind of see that the color's changing a little bit. We're getting the moisture into the aggregate. We just want it mixed up. And this is just a 2% content. Okay, so I'm looking at that and I think it looks pretty evenly distributed. We're going to do this process now. We're going to try to take this 2%, we're going to scrape it back into our bowl, or our container. Okay, so this is what's happened with just 2% moisture content to our aggregate. We are exceeding our container's capacity. So we're going to now update this to a 6%. We're going to add this back in here. You can already see that we have more aggregate now, volume-wise, than what our container can hold. We're going to add 4%, so that'll give us a total of 6% moisture content to our aggregate. I'm going to do the same thing. I want to mix so I have evenly distributed that moisture. You can see how the material is really kind of balling up in here. 6% moisture content is pretty high. We leave our stockpile untarped. If we have heavy rains, we have machine loaded and it gets a lot of water, gets rained on. Those are issues that affect the machinery. We need to understand it. So we're doing calibrations and we're trying to understand what our moisture content is. There's a reason for that. So now we have a total of 6% moisture content. 2% exceeded our container. So we're going to do the same process. We're adding in the additional 4. We're going to put it back in our container and just see what happens to our aggregate. So surface tension, right? That's where the water particles are coating the aggregate and keeping the particles from coming together. Well, let's just cut to the chase here. So you can see by volume how much more material we have with that 6% moisture content. When we are looking at the stockpile of our aggregates, you can pick up the aggregate and give a good squeeze to it, and you can get a rough idea of how much moisture content's in there just with a field test of seeing if it will snowball on you. If you open it up and it, after squeezing it tight, if it falls apart, you can get some rough field ideas, but the measurement is the process we've done here. We've completely dried the aggregate. We've added the moisture back to it to see what we've got here. So now we'll continue on with the presentation. Thank you very much.
I really have fun doing that live demonstration because it really is surprising of how much that moisture content can affect the volume of material that we're putting into the mix. Again, we've got a tight mix design. This tells us where we need to be for the materials down to a 0.5% of a sulfate. But yet our volume of aggregate can change significantly based off of moisture content. So kind of neat to see. It's important as we're looking at and trying to get the best performance of our materials. So here we're going to try to actually measure, how do we measure the moisture content? So we don't want to take a sample right on the surface of our stockpile because the surface obviously is either going to be wetter or drier than the greatest majority of the material. So here we've dug in just a little ways into the stockpile so we can get a more accurate measurement of what our a more accurate sample, I guess, of what the material is going to be in the stockpile as a whole. So we've taken our material we got out of the stockpile and we put it in a container. A container we can heat. In this example, we're using a metal container, and we're weighing it so that we know what our wet content is. Okay, we're going to we're just going to weigh the wet aggregate there. We're going to dry the aggregate so we can put it on a small heater. You can, obviously not in a metal bowl, but you can microwave the material to dry it out. You can put it in an oven. In a laboratory, the way it's done, they put it in an oven and they just keep checking it until there is no weight difference in it. So you've got sunshine, an oven, a heat source of some sort. So the process is we continue to dry the aggregate with periodic weight checks until we have 2 or more consecutive weight numbers that are basically, it just shows that you're no longer dropping in weight, and that tells us that we've got all of the moisture out of the rock. So we've gone through our heating process. Now we're going to weigh and document our dry aggregate. We're going to subtract the weight of the empty container. So to calculate our moisture content, so we've got moisture content is equal to the weight of the wet rock minus the weight of the dry rock divided by the weight of the wet of the divided by the weight of the dry rock. Sorry. So our example here, you see our little graph up here where we've kind of weighted, and we see where we're at on our weight trial. So we've got our moisture content equal to 1,000 grams minus 954 grams divided by 954 grams gives us a 4.8% moisture content. And it's a fairly wet aggregate. Now, I will have to say, with this virtual scenario, I'm not 100% sure how this part works, so bear with me. We're going to take this newly collected data and put it to use. Each of you will be given a worksheet. Hopefully, a worksheet will be sent to you. You're only asked to calculate the gate setting that has the weights that are in bold. Okay? It's just math. They just want you to try to understand the process. And we're going to do the same thing with the emulsion. So if you have the worksheet, you can follow along. Otherwise, here's the results. We'll walk through it. So we got the 65,260, the 59,540. So we got 5720 on our a 3-inch gate setting. Just kind of run through those. Right, because we already talked about this before. That was our last one. See, it's off by 20, well, over here. So it's off by 20 pounds on the last one. So we were at 5,700 pounds versus 5,720. So it's probably a scale swing. 5,713 on our total count, 98%, so 2% moisture content. And 55.99 would be what our dry aggregate weight would be. On the 4-inch gate setting, we come out at, we were at 78.1 on the first cycle, and we're 77.9 on the second. And we are at 78.3 on the third. Okay, those are all pretty darn close. Little swing variation, sometimes that happens. But when the average of the three comes out at the 78.1, with our 2% moisture content, our dry weight is 76.54. And we've got our 5-inch gate setting. We're at 98.87 on our first cycle count. We're at 98.667 on the second. And our third came in at 98.46. So our average is 98.67. So we added those three together, divided by 3. Our moisture content of 2%, so 0.98. So our dry aggregate is 96.69. Pretty simple process. We do have Excel spreadsheets that do all of this for you. They make it very, very simple. You just plug in the numbers and it does all the math for you and also creates a graph, which we'll show you in a minute. We need to input our emulsion calibration data as well. Let's kind of run through that quick because we've already gone through this. And that's at 14.4 average. There we go. So now we've got